So sum number 2.8, page number 2.93. In a parallel plate capacitor with air between the plates, each plate has an area of cross section 6 into 10 to the power minus 3 meters square, and the distance between it is 3 millimeter, which is 3 into 10 to the power minus 3 meters, and is a distance of 3 millimeter. Calculate the capacitance of the capacitor. If the capacitor is connected to a voltage of 100 volts supply, what is the charge? Okay, you know that the CQ is equal to C by V, and C itself is epsilon naught into A by D by V. So you know epsilon naught is a constant, A has been given, A has been given, D is known, and potential is known. You can calculate the charge, and it turns out to be 1.8 10 to the power minus 19 coulomb. And suppose you want only the capacitance, you know epsilon naught into A by D, that calculated value alone you can take, which will turn out to be 118 picofarad. You calculate and see. So then next is 2.9 question. Explain what would happen if the capacitor is given a 3 millimeter. After this, you're actually giving a dielectric constant of 6 is being placed, whose thickness itself is 3 millimeter. T becomes equal to D. Therefore, the new capacitance is K times C naught. If this is going to be the C naught, which is 18 picofarad, you have to just multiply it with a K, which is the dielectric constant, which is 6. And 18 6 or 108 picofarad will be the new capacitance. And you know when it's connected or disconnected, the capacitance will be 6 times. Whether it's after the stage you're connecting it or disconnecting, the capacitance will either way get multiplied. From the tabular column, you all know that. What happens to the charge? You know the charge is so much. When connected, charge will become K times, again 6 into 1.8 into 10 to the power minus 9. And when disconnected, it will remain 1.8 into 10 to the power minus 9. It's Q naught and it's K times Q naught, connected and disconnected mode, which you know. You can multiply and write the new charge. And regarding the potential, it's connected and disconnected. The connected mode, the potential will be just V naught. And whatever is the initial potential, if it's say 100 volts, it's going to remain as 100 volts only. And disconnected mode, it will be V naught by K, so 100 by 6. 16.6 volts would be the answer. This will be 100 volts only. So connected and disconnected modes. Very, very important question. So let's go to next question. Is the next sum that I did in the class is okay, I will want to do the fourth question. A spherical conductor of radius 12 centimeter has a charge of 1.6 into 10 to the power minus 7 coulomb distributed uniformly on the surface. What's the electric field inside the sphere? If you have, this is it a spherical conductor, is it hollow? Uniformly distributed on surface shows that it's definitely only hollow. And what is the electric field inside? You know the electric field inside of the hollow shell will always remain 0. Outside of the spherical shell is by Gaussian surface is 1 by 4 pi epsilon naught into Q by an R square. On the surface of the shell, this can be replaced by capital R square. Outside the shell means a small r square. And at the point 18 centimeter from the center means small r becomes 18. On the surface means capital R, which is radius. So just have to substitute and get those respective answers. Okay, let's go to next question. The third question that I want to do, two charges plus 2 microcoulomb and minus 2 microcoulomb are placed placed at A and B at a 6 centimeter apart, 6 into 10 to the power minus 2 meters. Identify the equipotential surface of the system. You know that the potential at the center will obviously be 0 at exactly the center because the dipole. Okay, because it's 1 by 4 pi epsilon naught into plus 2 microcoulomb by this distance, the whole square, this distance. And this will be 1 by 4 pi epsilon minus 2 by this half the distance, exactly the midpoint. They both will, because this negative charge and the dipole, this and this get cancelled. So potential at exactly midpoint between the dipole is 0. And identify the equipotential surface of system. Oh, they're not asking where the potential is 0, but they're just asking me the question, identify the equipotential surface, that's all. So you know, the equipotential surface will always be normal to the electric field. You know the electric field is going to emanate from positive and terminate in negative, which shows that since the electric field is in this direction, the equipotential surface will simply be in this direction. That's all. Identify the equipotential surface of the system. Yes, identified. What is the direction of the electric field at every point on the surface? It will be normal to the surface. So that answers this question. Let's go to next question, which is the second sum. You have an hexagon, it's a regular hexagon. What is the speciality of regular hexagon? All sides are equal. If this is A, and the connecting, these thing which are connecting is also in a regular hexagon will be just A. That's what it is. And you have a 5 microcoulomb of charge placed in the vertices of the regular hexagon. And the question is, the electric field inside will obviously be 0. But the question is not about the electric field, it's about the potential. There are 6 charges totally. So 6 into 1 by 4 pi epsilon naught into one of the charges by potential, which is A. It 6 times has to be multiplied because all of them will get added, because all of them are positive charges, no subtraction involved. So if you know the charge is 5 microcoulomb and 1 by 4 pi epsilon 9 and 10 to the power 9. If you know the A is 10 centimeter, if they have given A is 10 centimeter, you can substitute and get the answer to be 2.7 into 10 to the power 6 volts. And it's not a vector, it's a scalar, so then leave it like that. So let's go to next question. Sum number 1. There are 2 charges, plus 5 into 10 to the power minus 8 coulomb and minus 3 into 10 to the power 8 coulomb located 16 centimeter apart. At what point on the line joining the 2 charges the electric potential is 0? Nowhere between positive and negative charge electric field will be 0, but the potential can be 0 somewhere in between. And so let's see, it will not be midpoint because this is obviously a higher charge, a lower charge, so it's not midpoint, we can say it straight away. So you can keep this as x and this is 16 minus x. And the potential is 1 by 4 pi epsilon naught into 5 into minus 8 by x plus 1 by 4 pi epsilon naught into minus 3 into 10 to the power 8 by 16 minus x. Addition of 2 potential has to be 0, so therefore this is equal to this. So k into 5 into 10 to the power minus 8 by x is equal to k into 3 into 10 to the power 8 by 16 minus x. So cross multiplying it, 5 into 16 minus x is equal to 3x. 16 5s are 80. Minus 5x is equal to 3x and 80 is equal to 8x and x is equal to 10. So therefore it's 10 units. And this will be 16 minus 10, so 6 units. Centimeters. I'm not converting to meters because even if I convert into meters, it's 10 to the power minus 2 is going to get cancelled in the denominator. So I didn't have to, I just kept a 16x and 16 minus x. So this is the point at which the potential is 0. Do you think that's the only point at which the potential will be 0? No. Other than that, the potential can also be 0 on the right side of the minus 3. Whichever has got the lowest charge, come to the right side. So this will be, treat this as x. In that case, treat this as x. So let me redraw this. So you have a 5 into 10 to the power minus 8 coulomb and a minus 3 into 10 to the power minus 8 coulomb. I'm saying the potential at this point can also be 0. Let's consider this as x. This is 16 as we said. Let's consider this distance to be x. And the potential due to this is, the distance is 16 plus x. The potential due to this minus 3, it is x. So the distance. So then let's see. 1 by 4 pi epsilon naught into 5 into 10 to the power minus 8 by the whole distance, which is 16 plus x, can also be equal to 1 by 4 pi epsilon naught into that charge, which is minus 3 into 10 to the power minus 8, okay, plus minus 3 into 10 to the power minus 8 by that distance, which is x, can be equal to 0. The net potential can be 0 at that point, which means this is equal to this, minus and minus, the minus and all goes away. And so then you get 10 to the power minus 8 get cancelled and the negative sign goes away. 5 by 16 plus x is equal to 3 by x. So 5x is equal to 48 plus 3x, and so then 2x is equal to 48 and x is equal to 24. So then therefore it can also happen outside. Can you see? So then the potential can be 0 whether inside or outside, and so this is the way you have to think about. Similarly, I have also taught you another previous video where between a positive and negative charge, nowhere between them the electric field will be 0, but where can it be 0? Again to the right of the smaller charge. If this is minus 3 into 10 to the power minus 8 and this is plus 5 into 10 to the power minus 4, it's not about negative or positive, the magnitude of the charge to the right of it. You can consider this as x and this is 16. And so here again the electric field can be 0. There, electric field can be 0 only at that point between positive and negative charge. It will be located exterior to the positive and negative charge. So let's go to the next question. The next question is about Problem number 34. Problem number 34 is page number 2.89. Okay. A four-point charges are placed, capital Q, small q, capital Q and a small q, on the vertices of a square of side A. What is the electric force on the charge Q? This Q. This Q is going to repel it like this. This small q is going to repel it like this. And this capital Q is going to repel it like this. There are three forces acting. But the best part about it is, can you see this is small q and capital Q. And this force is therefore K into Q into capital Q by A square. This will also between small q and capital Q. So K into capital Q small q by A square. But this is between Q and Q. So it's K into Q square by the diagonal, the distance. This is root 2A. So root 2A means 2A square. That's this. You calculated this force and this force which are equal, and this force which is the diagonal force which is different. And you're going to resolve it as vectors. Can you take this and this alone? The resultant will be in this direction, which is root of this square plus this square. Okay, so KQ capital Q A square plus KQ capital small q by A square. This is the resultant force, and which has to be added to the force of the diagonal. The diagonal force has to be summed up. You have to add this force with this one. Okay, and then write the whole answer. I am sure you understood. This is a way to resolve this question. Okay, so then if you're going to do the sum, can you see here? There will be K square which will come out as K, Q square which will come out as Q, capital Q square which will come out as capital Q, and A to the power 4 which come out as A square. Root of 1 plus 1 will be just root 2 because I'm taking everything out, so I'll get a root 2. And this is the net force of these two resultants. And already you have this along the diagonal, you have to add it with this KQ square by 2A square. And the total force will on the capital Q will be this. So this is the way you have to resolve it. So what is the next part of the question in this? It's the potential energy of the system. That's a beautiful question. The potential energy's formula is 1 by 4 pi epsilon naught into Q1 Q2 by R. So then the 1 by 4 pi epsilon naught into, I'll do it in green color if you want, capital Q into small q by A. 1 by 4 pi epsilon capital Q into small q by A. 1 by 4 pi epsilon capital Q into small q by A. 1 by 4 epsilon capital Q into, so it's coming 4 times K into capital Q into small q by A. And apart from this, there's also potential energy between this and this. Can you see the diagonals? Which will be K into Q square by diagonal. Because potential energy will have only R, so root 2A. Plus apart from this, you'll have this which is between small q, which is K into small q square by again root 2A. The total have to be added. The total of all these potentials will have to be added. In that case, I'm sure you understood. The potentials formula is simply 1 by 4 pi epsilon Q1 Q2 by R. If it's negative, you have to write it as negative. Okay. So let's go to the next question. The next question I did, this is a star case sum, where is sum number 33. You have a capacitor which is made up of a flat plate of area of cross section A, and this is a second plate which is like a star case, twang, 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 like this. If this is A, this is A, this is A, obviously this length will be 3A. And you can imagine the plate has got cross section area A. This area will become A by 3, this area will become A by 3, and this area will become A by 3. And therefore you are able to locate, and this distance is given to be D, and this distance is B, and B is not, it's just a distance, okay, it's just a separation is increased. So for there are three capacitors, C1, C2, C3. For the first capacitor, the separation is just D. For the second capacitor is D plus B. For the third capacitor is D plus 2B, you know. So then that's what it is. So let's write the capacitance, which is C1 itself is epsilon naught into A will become A by 3 into D. For the second is epsilon naught into A by 3 into D plus B. For the third, it's epsilon naught into A by 3 into D plus 2B. And you know, if you're going to assume this is positive, the entire other end will obviously be negative, and it's like negative and negative is connected. It shows that they're parallel connection. In a parallel connection, the equivalent capacitance is C1 plus C2 plus C3. Hence, you have to add 1 plus 2 plus 3 and you get the total answer. I'm sure you understood. So let's go to the next question, which is sum number 32. You have a Y-shaped capacitor like this. You have a parallel plate like this. and this point is P, you have another parallel plate like this point is Q. If this is given a positive potential, this is given a negative, the whole of this plate will be positive, positive, positive. The whole of this will be negative, negative, negative. This separation is D. Okay, so then can you see, because there is a negative, can you see capacitance, positive plate, negative plate, you have capacitance 1, you have a negative and a positive, capacitance 2, positive and a negative, so this is capacitance 3, there are 3 capacitors, and in this case bit intervening you have a negative connected, which is parallel, and here it's positive and a positive connected, so these two are parallel. So therefore you know C1 is parallel to C2 is parallel to C3, and therefore C is equal to C1 plus C2 plus C3, which is epsilon naught into A by D plus epsilon naught into A by D plus epsilon naught into A by D, which is 3 times epsilon naught into A by D. So that's this question. So let's go to next question. This is sum number 31. Sum number 31, you have a different Y shape, you know, the extremes are connected like this, and this is your point P, and in between it's connected like this, and this is your point Q, and it's giving positive, this is given negative potential, then this plate is entirely positive, this end plate is entirely positive, this will be negative and this will be negative. Can you see this is a capacitance C1, this is a capacitance C2, this will not even form a capacitance, because it's negative and negative, there is no capacitance in between. So there are only 2 capacitance, and how are they connected? A positive is connected to a positive, which shows that's parallel again, and so C is equal to C1 plus C2, which is epsilon naught into A by D plus epsilon naught into A by D, which is 2 into epsilon naught into A by D. So you should understand how to identify the structures. Okay, let's go to 30th question. The 30th question has got a capacitor like this. Look at this diagram. There's an A which is here, the plate A, and there's a plate B. Exactly divided like this, keep it like this. Fill it with the dielectric constant K1, this is with the dielectric constant K2, this is with the dielectric constant K3, which makes it a capacitor C1, C2 and C3. Since this is connected to positive A and this is connected to B, assuming this positive negative, just assume, then this whole plate in here will be positive, this whole plate in here will be negative, the B's end, and therefore each one should have form a parallel plate. If this is positive, this will become negative, and since this is negative, this other end would become positive, and between this and this it becomes like a series connection, because a negative and a positive is connected. Therefore C2 and C3 are in series, so it's C2 C3 by C2 plus C3 is the equivalent capacitance when it's a series. And the C1 and this entire setup is going to be in parallel, because a positive and positive is connected, which shows that C1 plus C2 C3 by C2 plus C3 will be the equivalent capacitance. That will be the equivalent capacitance of this entire. So let's calculate, can you see it's exactly divided halfway. If this plate is A, then obviously this will be A by 2 and this will be A by 2. It's been given that this plate has a distance separated D by 3 and this is 2D by 3. Okay, so then therefore you can calculate each and every capacitance. What does C1 stands for? C1 is K1 into epsilon naught into A by D. No, A is also getting divided by 2. It's A by 2 into D. Because separation is remaining to be D, but area is A. Let's take C2. It's K2 into epsilon naught into A is A by 2. D itself is D by 3, so 3 goes here. Capacitance C3 has a dielectric K3, so K3 into epsilon naught into A by, again it's divided by 2 area. D is 2D by 3 and therefore you get a capacitance. Each capacitance is different. This will become 2 2s are 4. So these are values of C1, C2 and C3. You have to plug it in and find the equivalent capacitance. So therefore you have to plug it in and find the equivalent capacitance. Such a beautiful question. So I hope you are all understanding. Please do the sum as per given in the Aurora and complete the sum. So let's go to the identification of how which is parallel, which is series is what is very important. As long as you understood that, it's fine. Example 29. Problem number 29. You have a plate of parallel plate capacitors like this, where this has got a dielectric medium C by C3, C2 and C1 with the dielectric medium K is equal to 2 for this medium, this alone. C1 alone has got a dielectric. This is a metal copper. C3 doesn't have anything, which means vacuum or air. This is D by 3, D by 3, D by 3 of equal width. So D is a total separation. So this is the diagram between the plates of the parallel plate capacitor of area A. So the area of cross section of this is A, the area doesn't change and this area remains the same throughout for every capacitor. A copper plate is also inserted, dielectric slab is also inserted, some point there is vacuum, the equivalent capacitance of all this. Okay, so let's see, if this is a positive plate, obviously the other end will have to be negative. If this is got to be negative, let's see what's happening between, this will be negative. Since this is negative and the other extreme, this has got to be positive. So you have a capacitor C1, you have a capacitor C2, C3, and let's study that. Okay, sorry, I'm writing it wrongly. C3, C2 and C1. 3 different capacitors, but let's see the polarity, understand which is in series and parallel. Can you see? This is negative and negative is connected. So this is in parallel. C2 and C3 are parallel. And this is like positive and positive is connected again parallel. So they're all parallel. Am I saying the right thing? Let's check if they are parallel or series. Let me study it once again. So you have this end, this is the one end and this is the other end. And if you're going to assume that this is completely positive, this end has to be negative. And if this other end is going to be negative, then this has got to be positive. And definitely you have therefore 3 capacitors undoubtedly. In this, a negative and a negative is connected. This a positive and a positive is connected. And let's go back and study this one. What did I say here? This end is completely positive. This end will be negative. Because of that, the near end, this will be negative and this will be positive. And so you're getting, if I'm going to apply this phenomenon here, sorry, I have to apply this phenomenon. Okay. So if I apply this same phenomenon here, this is positive, this end is negative. And this end, so this is positive. This has got to be, say this end is positive, this end becomes negative, and this end can become positive provided they are connected to positive voltage. Okay, depends on what they are connected to. One second, hold on, I want to redo the sum. Okay, where a copper plate of dielectric slab, find the equivalent capacitance of this arrangement. This is positive, see. This is going to be positive. This has got to be negative. And this is going to be negative. Then this has got to be positive. And the area, this it is positive is negative, this is negative. See,